All right, so now let's look at a detail that usually doesn't get much attention from students who are working on inverse functions. Okay, so let me now erase the board here, and I will mention that what that detail is. All right, so you can always roll back to that earlier part of this lecture here where I gave out that definition of what inverse functions are, or how any two functions are said to be inverses of each other. Okay, you can roll back to that definition point, and I wrote down the following remarks right here. So, of course, I am not going to repeat that definition, but I'm talking about right after that definition, I wrote down the following remark. So at this point, let's say we're gonna have any two functions, but we know they are inverses of each other. So let f of x and g of x now allow me to avoid, in this particular case right here, allow me to avoid using the f inverse symbol right here. So just any two functions. But now let's say we know that they are inverses of each other. So let f of x and g of x be inverses of one another or each other. Okay, so the remark I wrote down earlier is as following. I already wrote down this remark after we looked at the definition of inverse function here. So now if f and g are inverses of each other, then of course g is the inverse of f, and f is the inverse of g. That's what I meant like that. So in that case now, the domain, this is what I wrote. So number one, the remark number one that I wrote as the first bullet point right here, bullet remark right here, the domain of g. If g is the inverse of f, then the domain of g is the range of f. Okay. F of x. And then the range of g, okay, is the domain of f of x. And then the other way around. Okay, I believe I only wrote down the domain and the range on the inverse function. And so if g is the inverse function of f, then the domain of g is the range of f. Okay, and then on the other, and then likewise or similarly, the range of the inverse function is going to be the domain of the original function where it came from. Okay, so this information, as I said earlier, this detail, as I said earlier, when I start introducing it, it's natural that way that I also try to make it small detail, to make it look like a small detail, so that anyone first time learning about inverse function would turn all of their focus into understanding what a function is. But now it's a good time to dive into this particular detail right here, because surprisingly it will bring good usefulness for the later part of this lecture. And also it's a very useful information for the later courses immediately after this pre-calculus course. A lot of you will be enrolled into a trigonometry course or even calculus and higher. Those are the classes in the future of yours that will utilize this understanding a lot right here. So now it's a good time, after we have already understood fluently and work fluently with and be able to work fluently with inverse function and how to find inverse functions and all that. And now it's a good time to dive into this particular detail that, like I said, usually does not get much attention from students who are working on inverse function. Okay, and so now allow me to, so I'm going to leave this here. Allow me to get on the other board, and I'm going to bring an example, and along the way I will be explaining how important this remark is. So I gotta clarify, but the example I'm about to bring up here is not even a formal example where I put that with where I label that with a number, like example 4, example 5. It's more like a demonstration problem of the idea first, and then we will get into an actual example. Okay, so let's look back. Let's look at the following function. Okay, so I'm gonna have f of x equals 5 over x plus 4. Okay. You may recognize this function or you may not. That's okay. But I'm sure I brought this problem into one of our earlier example as a problem where we were making our attempt to find the inverse function. So this was one of the problems where we were working out steps to find the inverse function of this particular problem. Okay, it's a one-to-one function, and we can use the graph to verify that. Okay, but now what I'm about to blend in as a further detail, but quite important. It seems like it's just additional detail, but it's very important. Any function has a domain. Any function has a domain. So this is the information that when I was showing the steps to find the inverse, I did not mention much. But now it's time to really look into that kind of details again. So this function, on our way, we have learned prior to this lesson about how to find domain of a function. And so you can pause the video at any time to double check with my result right here. But this function, in your understanding at this point, you will know that the domain of this function is the interval in interval notation, is the interval anywhere from minus infinity to 0, anywhere between minus infinity and 0, and then with another interval between 0 and positive infinity. That's the domain of this function. This is the set of all possible input values of this function. Okay, and again, you can feel free to pause the video and apply your skill that you've learned previously prior to this lesson. Apply that skill to find the domain to confirm the result I'm writing up here. I'm saying that this is the domain of our function f of x equals 5 over x plus 4. Okay, and then so along that way, you can also use the graph to investigate that the range of this function is that interval anywhere between minus infinity and 0 and actually 4, okay, between negative infinity and 4, and unions with the interval anywhere between 4 and positive infinity. Okay, and so when I was teaching about how to identify the range of a function, I approached that graphically. So this function is simple enough that you can quickly hop into any graphing utility like Desmos that I've been using quite a lot throughout my lectures, or your graphing calculator, the TI-83 or 84, or even the Casio or the HP graphing calculators. Any of those can get you the picture of your graph, and from your graph, you can quickly identify the range. You can quickly be able to tell the range of your function. So you can, once again, you can pause the video and use a graphing utility, okay, to confirm what I'm writing up here, that the range of this function is the union of two separate intervals. And one interval is between negative infinity and 4, and then the other interval is the other interval is 4, between 4 and positive infinity, and it's a union between the two intervals. So that's the range of my function right here. And so we spent our time working, and we came down to f inverse. Okay, we came down to f inverse being 5 over x minus 4. So we came to that conclusion when we were in that example where we particularly apply the steps to find the inverse of our function after verifying that it had an inverse. It was having an inverse. And so we found this inverse right here by following our steps, our guidelines. But then now at this point right here, I have to also mention, so in this case, the domain for this case now, the domain of this inverse function, this f inverse right here, the domain of this f inverse, not that one, but it's actually this right here, because according to the remark I had up here, which I introduced already, but now it's time to emphasize that the domain of any inverse function is the range of the original function where we found that from. Okay, and so that means in this case right here, the domain of this inverse function is that interval anywhere between minus infinity and 4, okay, in union with that interval between 4 and positive infinity. That's one important information. And it will be, I mean, right now it's instead of applying our skill on this particular function to find the inverse, I mean to find the domain of this function, we can bypass that, and we can just quickly use that understanding we've had that I've written down on the other board, and then we can quickly come up with the domain of this inverse function instead of doing the formal math and find the domain. And that's one usefulness so far of having that understanding with us. And so in that way, similarly, now looking at the range of this particular inverse, okay, after we knew the domain of the original function, everything here is the original function, and then starting this point down, I'm looking at domain and range of the inverse. But now we don't need to do the graph. We don't need to do the graph for this this inverse function. We already knew the domain. We didn't have to do any math. We didn't have to draw any graph. And now getting into the range, again, we don't need to draw the graph to identify the inverse. That was admittedly the technique I've shown a lot of my students to use for identifying the range of a function. But now in this case, since we already knew that this function is the inverse of this f of x right here, and so we already found the inverse of f of x to be having this domain right here. We already found that this function f of x has this domain. And so now its inverse, on its inverse right here, the range has to be that domain. Okay, so in interval notation, we're looking at minus infinity to 0, and unions with 0 and positive infinity. Two separate intervals union together. And that gives our range of this function. All right, so this quickly demonstrates the idea right here. And now let's get into a formal example so that you see, so I'm bringing up the domain and the range of this inverse function after we have already found that by applying the steps to find the inverse. So it's a little cheating right there. So now I'm going to purposely get you into an example where you can see as far as the steps. Think about if we were on our way to find the inverse of a given function, provided we already knew it will have an inverse, then as we are on our way to find the inverse of a function, which steps, how do we fit in these steps right here as well as, aside from finding the inverse, we can also find the domain and the range of the given function. The domain and range of the inverse function that we're about to find. Okay? All right, so now let's get ourselves into that example. All right, so here we are at example 5 right here. Okay? So now I'm going to get straightforward into the wording right here. Find the inverse of each given function. Okay, and it's a domain and range. All right, and so I gotta clarify when it say its domain and range, I'm talking about the domain and range of the inverse. All right, so here's the idea. I want to show the foremost steps in this example so that, hey, you having a function f of x given, we will be applying our steps, which you already learned, which you have already learned. We're going to apply that steps, that guidance, to find the inverse. And along the way, I'm going to show you how we can fit in the steps to find the domain and the range of that inverse. So its domain and range, I refer to the domain and range of that inverse that we're on our way to find. All right, so here we go. Let's dive in. And so now allow me to bring back that guideline on the screen as well. All right, so I spent some time at the desk, computer station desk of mine to prepare that notes about the general guidelines. So I will bring it up on the screen here after I finish writing down the problem. So now I'm going to have a function f of x given as about 2 minus square root of x. 2 minus square root of x. Okay? And so let's get straight to the point here. This function is one-to-one because the intention behind the scene that it goes a little loosely. Here that we are supposed to verify if this function is one-to-one before we can find the inverse. But here it's already kind of without formally indicating for us that this function was already one-to-one. So all we have to worry about is to find the inverse. Okay, but you can always pause the video and make sure this function is one-to-one. Okay, but now assuming that this function has already been verified to be a one-to-one, we want to find the inverse. Okay, so but then aside from finding the inverse, we also need to find the domain and the range of the inverse of this function. So this function has its inverse. We want to also find the domain and range of its inverse. That's the idea right there. So how can we blend that into the steps that we were doing earlier? Okay, so now formally speaking, at this point we need to recall for ourselves, or we need to find for ourselves what is the domain and the range of this particular starting function first. Before we find the inverse, we got to find the domain and range of this function. Okay, and so now with your past understanding, with your understanding from previous lecture of how you find the domain and range, so now allow me to skip that work. I just simply show the final answer right here. This function has the domain. This function has the domain anywhere from 0 to positive infinity. This function has that domain anywhere positive as an interval, anywhere from 0 to positive infinity. Okay, and I can verify that at least without showing the proper reasoning, but I can still show the graph here. All right, so in the blank graphing space right here, this is our function 2 minus square root of x. This is our function 2 minus square root of x. And so apparently, again, if we can focus right on these horizontal lines right here as the grids, then it proves, it clearly shows that this function is a one-to-one function. Okay, so that's just a quick brief back right there. But that's not important. The thing I need to discuss right now, in the way how this function appears graphically, then the domain is anywhere, see the horizontal spreading of this graph is anywhere that starts at x equals 0, and then it keeps spreading to the right-hand side, and that's how it confirms. That's how it confirms that this domain, this function has a domain that goes anywhere from 0 to positive infinity. Okay, so that's the domain. This same function has the range. So because the problem is also asking for the domain and range of the final inverse function, so we gotta also track down the domain and range of our beginning function. That's the idea right there. Okay, so it's a little bit unlike the earlier example I did where I applied just the steps to find the inverse. Here I have to also, aside from applying the steps to find the inverse, I also need to keep in the side of my work all the way through the domain and the range of this beginning function. All right, one more time I'm going to swing back at the graph. So now with the graph of 2 minus square root x, this function here has the domain that goes anywhere from, see, it keeps spreading down right here vertically. But it does vertically stop, this graph in red right here will vertically stop at y equals 2. Okay? So that means the range for this function is concluded to be anywhere from minus infinity to positive 2. That's the range of this function. All right, so now let's just leave that piece of information there. All right, so now we're gonna, once we know the domain and the range of the beginning function, now we're gonna start applying the steps to find the inverse. And again, because you have seen the steps, you have seen the function earlier, it's clearly a one-to-one function. So we will be able to find the inverse successfully. All right, so step 1. Allow me now to turn on the general guideline right here to remind anyone. All right, so step 1, we're gonna replace the f of x symbol here, okay, with the y variable. So it's y equals 2 minus square root x. Okay, with that step right there. So nothing needs to be done with the domain and range. So I'm going to leave it there in that corner. That's the first step. And then now the next step, we're going to interchange. And so interchange here, interchange the x and the y. And that is for the next step right here. All right. So from this current step, the next step now is to interchange. So this equation becomes x equals 2 minus square root y. And this is where, in my personal style of teaching, I prefer that student can start bringing in the domain and range information at this point right here. This step number 2 right here is important. When you swap the x and y, the domain and range is going to start swapping as well. So this is the domain and range of the beginning function. This is the domain and range of the beginning function. But now allow me to swap, so I'm going to use a different ink. So for this step 2 right here, since x is swapped, is switched to y is switched to x, and x is switched to y, so now I'm going to write the following. Just something to remind me. But see, this blue version now is going to be the eventual domain and range of the final inverse function. So now they switch role. See, x becomes y and y becomes x. So the domain was corresponding to x, but now x becomes y. So that would become the domain, and that would become the range right here. So now the range earlier for y, now it switched to x, so now the domain is negative infinity to 2. That is the domain of this at this step right here. All right, so once again, it's the logic here simply because we switch roles of x and y in from our current equation. We switch row of x and y, so that means the domain, again, the domain is corresponding to the x values and the range is corresponding to the y values. So now y switched to x. That's why the range previously now switched to domain. And then the domain previously now switched to range. Okay, so now I have, so the range here will be tentatively that interval from 0 to positive infinity. All right, so that is the domain and range, and I had to write that in blue ink right there. Okay, so now I'm gonna bring down, and it will be hiding this information behind the scene a little bit, but take good note of that, because as I pull up that steps to work on the domain and range, I mean the steps to find the inverse, then it's going to hide, this information is going to be hidden behind that little extra note. All right, so now I'm going to continue. So solving for this equation for y. Okay, so we're going to have, I'm going to rearrange this equation here as square root of y to equals 2 minus x. Okay, that's just rearranging the term. That term is added to the left-hand side, and then this term here is subtracted to the right-hand side. And that's how I ended up with that. And then now from this point, I am going to square both sides to solve for y. And that's just familiar with what we were doing. And so at this step right here, I am solving okay, for y. That's the current step starting here. All right, and so now solving for y, I'm ending up with 2 minus x all square. Because to solve for y, I need to square both sides of this current equation. And that's how I ended up. And so now my final concluded inverse function. Now I can write, hey, inverse function, f inverse of x, should be that 2 minus x all square. This is my final inverse function. Okay, and I do realize it's a little squeezed in my writing. It's a little squeezy in my writing right here. So f inverse, all right, f inverse of x equals 2 minus x all square. Okay, and that's our work right there. All right, and now once we have arrived at this final inverse, look at the information in blue. So this function here will have that information, the domain and range information. So now I can hide the steps away. All right, so this domain and range in blue is the domain and range of this particular function right there. All right, so now the final inverse function is this 2 minus x all square, and then the domain is claimed, right, was found to be anywhere between anywhere from negative infinity to 2, and then the range of this inverse function is anywhere from 0 to positive infinity. Let's use the graph to confirm our understanding. And that's only, but at least this is the end of part A right here. And then I'm going to bring up the graph to confirm the results. All right. All right, so now on my blank graphing space right here. All right, so now on my graphing space right here, this graph in red is the graph of 2 minus square root of x. That's the graph for 2 minus square root of x. And then here's the 45-degree line. So the inverse function will have the graph that's the mirror reflection of this red graph, but through the 45-degree line. And so this is the graph for, so this is the graph for 2, and the graph in blue right here is for 2 minus x all square. And yes, that piece of information, see, it's not the entire, it's not the complete piece, it's only the piece that takes value from, as far as the domain, anywhere from negative infinity to 2. That's why the piece in blue right here looks consistent with our understanding of the domain. Yes, it's just a, if we're looking at that, it's just a quadratic like any other quadratic, but it does not take the entire domain. It only stays in that domain anywhere from minus infinity to 2. And that's consistent with what's showing on the graph right here. That's what's showing on the graph. Okay, and then now as far as the range, okay, so the range, and I still keep that graph here on the board. It's hiding my some of my blue writing right here. So the graph here in blue has that is only anywhere starting from the x-axis and up. Okay, this graph in blue right here vertically is only anywhere starting from the x-axis and up. That means it's consistent with the fact that the range we have found already being anywhere from 0 to positive infinity. And that's how we get the problem done. The first problem done, we found the inverse function, and along the way we found the domain and range of this particular inverse function. All right, so now once we are in gear with this kind of problem right here, okay, let's advance to part B, and I can start picking up the pace a little bit. All right. So here is part B of our example. This is part B of our example. So let's look at, how about a function, and I can call that with a different name. So g of x to be the function. And how about it's 1 over square root of x minus 2. 1 over square root of x minus 2. Okay? And then we want to find the inverse of this function. So at the final end, we're going to have to call it, it's the g with the superscript minus 1 symbol. This is our final answer right here. That's what we want to find. We want to find what that expression is, what that function is for what we call g inverse. Okay, but so right now we're on our way. But then this example is not only looking for the inverse of this function, it's also looking for the domain and range of the inverse. Okay, and so now before we start, we gotta know the domain and range of this function, this beginning function g of x. And so now allow me to introduce again. I don't think I need to show the formal math. You can always pause the video and work on apply your skills to find domain and range of any particular given function. Okay, and then double confirm the results with me here. But the domain for this particular function is an open interval completely from anywhere between 2 and positive infinity. That's the domain of this function. Okay, it won't even include x equals 2 in this domain. All right, and then shortly later on, as I start getting into the problem, I will also show the graph, which will also confirm graphically about the domain of this function. But I won't show the steps algebraically to find the domain here. I'll leave that for my students who learn this lesson from me. Okay, and then in the meanwhile, the range of this function. The range of this function is anywhere between 0 and positive infinity. And now for the range, I can pull up the graph to easily verify the range as that interval, the range being the range of this function right here. All right, so let's have a look at the graph right here. All right, so now on our empty graphing space right here, let me now put in the graph for f of x. So this graph in red right here is the graph of f of x. Okay, and so now with the graph of f of x here, clearly we can rely right here with the horizontal grid lines right here, and it says clearly that, it verifies clearly that this function has an inverse. Okay, because it's 1 to 1. And now furthermore, by looking at the horizontal spreading of this graph, we can see clearly that the domain of this function is anywhere between 2 and positive infinity, because it's only to the right hand side of the vertical line x equals 2. Okay, the graph tells that story already. And now with the range, as I have said earlier, so now in this picture the range is showing the vertical spreading of this graph is showing anywhere between 0, the x-axis, and up. Okay, and that is the reason why it's consistent with the intervals indicated here. Anywhere between 2 and positive infinity, that's the domain. Anywhere between 0 and positive infinity, that's the range of this function. Okay, and so now we're going to use this information and we're going to start finding our inverse function and then the domain and range along the way. All right, so now I'm going to draw a little space right here. So at this point you have seen enough the guidelines right there. So allow me to skip that. So now in the first step, I am going to replace the symbol, this g of x symbol, the functional symbol, with the variable y. So y equals 1 over square root of x minus 2. Okay, and at this step, that's the only action we need to take. Okay, and then in the next step, we're going to interchange, or we'll swap roles between x and y. So x becomes y and y becomes x. But that step is critically important. X becomes y, so this is 1 over square root of y minus 2. And then the y becomes x. That means the domain and range from our original function will now also switch role. This interval, which was the domain of the beginning function, now that interval will become the range of our inverse to be. Okay, and then this one's being the range of the original function now will become this was the range of the original function. Now it will become the domain of the going to be inverse. Okay, so now I'm going to write that down. Now in blue version right here. So for the domain of the inverse going to be, it's going to be anywhere between 0 and positive infinity. All right, and then the range, okay, is switched to 2 and positive infinity, anywhere between 2 and positive infinity. All right, and then so that critical step is here, when it will remain the same for the rest of the steps, like that. And so now we're gonna continue solving for y variable as the third step. So solving for y variable, from here I am going to take the reciprocal on both sides of our equation. So now I'm looking at 1 over x equals square root of y minus 2, okay? And then some more algebra step. Now I can erase this information I've kept on this board long enough. All right, so now at that current step, 1 over x equals square root of y minus 2. In order to solve for y here, I need to take the square on both sides of our equation. So now this is y minus 2 equals 1 over x all square. Again, as I said, I took the square on both sides. I squared both sides of our current step here. And that led me to this 1 over x all square equals y minus 2. And so now we're ready. Y equals 1 over x squared plus 2. I added that 2 to the other side. Okay, well now I can write that now as the inverse of g. And you also have your choice to bring this equation back to the friendly friendly version, which is y equals 1 over x squared plus 2. But now 1 over x squared plus 2 is our inverse function. It's our final inverse function. But now this inverse function, in what we have found, this inverse function has that domain being the interval anywhere only between 0 and positive infinity. And the range of this interval, the range of this function is that interval anywhere between 2 and positive infinity. All right, and so now in that way, let's use the graph to confirm. All right. So now back in my graphing space right here. This graph in red currently is the graph for our g of x, which was 1 over square root of x minus 2. And now I'm going to put in the 45-degree line for us to think of that as the mirror over here. So now, as expected, the graph of the inverse function will be will be the reflection of this red graph through this 45-degree line. But now getting that sketch is not easy. So let's allow machine to handle that. But this is now the graph of our inverse function. So this graph in blue here is the graph of 1 over x squared plus 2. Okay, 1 over x squared plus 2. And now let me hide away the graph of the original function and hide away the 45-degree line. So this is the inverse function. Right there, 1 over x squared plus 2. Obviously, it shows that the domain and range from this picture looks to be consistent with what we have found right here. The domain is anywhere, and as you can still see from the picture, the domain is anywhere between 0 and positive infinity. That's the reason why the graph is only on the right-hand side of the y-axis. And then now the range is anywhere from 2 to positive infinity. Indeed, excluding 2, right there, anywhere only between 2 and positive infinity. And so it shows in the graph right here that we have a horizontal line, and this graph never hits to equal y equal 2. We never have that y equal 2. It's only anywhere above 2 and even above. All right. And so now before we're done, before we're completely done with this example, let's look at an FYT problem. Okay. So let's call that h of x, and I want students of mine who are learning from this lesson find the inverse of this function on your own and also find its domain and range right here. So how about h of x equals, it's a square root of 2x minus 8. Okay. So go ahead and pause the video, spend your time working on that, apply the steps and follow the instruction I've had in the earlier problems like that. Have your own problem done and try it out like that. When you resume the video, I will only show the domain and range and the inverse function of this particular function like that. Okay? All right, so now at this point, assuming you have already had some work done with them, so the inverse function for this, h of x, will be 1/2 x squared plus 4. All right, and then the domain of this function will have domain anywhere between 0 or from 0 to positive infinity. And this function here will have the range anywhere from 4 to positive infinity. All right, and that's how we have done this FYT problem. All right, so at this point we are going to advance into even further details about inverse functions. So before we get into this later part of the video lesson, here allow me to further recommend to view this lesson, this later part of the lesson here after you have mastered your skill on piecewise function. So it is highly recommended. As a matter of fact, it is required that you know about piecewise function, so that we can move into this particular the later part of this lesson on inverse functions here. Okay, but so now what are we looking into? What further details are we looking into? All right, so now everything from the beginning of inverse functions up to this point, everything I've been saying is based on one-to-one function. Yes, a function can only have an inverse when it's a one-to-one function. A function here has to be one-to-one function in order to have an inverse. We hear that term one-to-one function all over. Okay, but now sadly, there are a good percentage, there are a good amount of functions out there that are not one-to-one. There is a high percentage, there's a high proportion of functions out there who are not one-to-one. So what about them? So what about those functions who are not one-to-one? Does that mean they will never have an inverse? If that's so, if that's the truth, they will complain. Those functions that are not one-to-one, they are going to complain. I mean, how come only the one-to-one functions have inverse, and then not us? Even we may even take a larger majority of functions out there. It sounds like a joke, but it raises a concern that what can we do to overcome this problem? What can we do to overcome this the challenge here, this dilemma that function to take the inverse, we can only have inverse for one-to-one functions. So how can we overcome this difficulty, okay, or this limitation? All right, because now the reason I mentioned that, because you can look right among your toolkit functions. Just briefly look back at the toolkit function. And so hopefully at this point, anyone viewing this lesson is fluent enough with deciding whether a function is a one-to-one function or not. So among the toolkit function, this constant function is already failed being a one-to-one. Only the special function y equals x, the identity function, is one-to-one. Then we had another toolkit function, the absolute value function. One common one among the toolkit function. This function fails being a one-to-one function as well. So we already had two failed candidates. Failed means they just not one-to-one. So for now, in a way how we understand currently, they won't have inverses. Okay? What else can we think about among the toolkit functions? So I erased that identity function. The simple quadratic function, another failed candidate to have an inverse, because this function, in a way it fails a horizontal test. So it's not one-to-one. Okay? And then we also have another function. How about this function here? All right. I cannot make the best shape out there, but this function is the quadratic. This is the reciprocal squared function. F of x equals the reciprocal square, 1 over x squared. It's another candidate that failed having an inverse. Okay. It's already made up a large proportion, a large percentage among our toolkit functions. These are the toolkit functions, and I only mentioned a few, and it already showed a good percentage of those functions fail to have inverse functions. So does that mean we're gonna ignore them forever and never gonna even bother finding the inverse for these guys, or for these not one-to-one functions? Nope. So now we're going to learn a technique right here to overcome that limitation, to overcome that challenge right here for us, so that any function now from this point on we can somehow find an inverse function on that. All right. So now allow me to navigate to the other board, and I'm going to bring up that this quick little demonstration problem right here. Okay. So now, it's not a formal example yet. It's not an example. It's only a demonstration to illustrate the idea. All right, so now let's look right at that function f of x equals x squared. It happened to be my favorite function to work with, and it's not too straight like a straight hard line, like the absolute value, and it bends and it forms into a nice parabolic shape right there. So I choose that, and it fails to be one-to-one. So let's purposely focus on that function f of x equals x squared. F of x equals x squared. Okay, so let's look at that function. So how about I would say consider, because right now we want to just do an illustration, a demonstration that illustrates the idea. Okay. So with this function, obviously, it fails to be one-to-one. Okay, and let me show that on the graph. Now with our blank graphing space right now, this is the graph for f of x equals x squared. All right, it has that graph, and this is the reason why it fails having an inverse, because the first important thing, it fails being a one-to-one function. All right, because see, if we're looking at any horizontal grid line right here, we have already found so many grid lines, horizontal lines that crosses through the graph at more than 1 point. Okay, and so in that way we can do the following trick right here. Okay? In that way, we can do the following trick. Now, the reason I get back on the board here, instead of keep staying with the graph here, is I want to mention a couple things. So things starting to get a little advanced, so be patient as you're following with this later part of the lesson. But so any function, in the way it is, at least with these functions where we already saw a predefined formula like this one, or f of x equals 2x minus 1, or f of x equals x squared, we saw a written rule that's written by mathematical operations. So here we got the square operations. Some other function we have, say some other function g of x, we have a 3x minus 1. See, there's subtraction and there's multiplications being involved. So those are the mathematical operations. And so any function, not only this one, not only that one, but now in my own terms, I tend to explain to my students that for any function in the way how it's defined based on the mathematical operations that's involved there, any function has its own natural domain. That's probably just the term I'm using on my own right here. Any function, okay, based on its own way how we define it, depending on the way how we define the function, and based on its the mathematical operations that involved in a function. Okay, so any function has its own natural domain. That's how I call that. Okay, meaning it's just or sometimes you can think of that as the default. Okay, the default domain. It's just the kind of domain that comes straight out naturally from the way how this operation defines. Okay, so that means we have looked back. We can just simply look back into this function as a toolkit function, as what we know. The domain of this function, the natural domain, is simply in interval notation, minus infinity to infinity. It's not like anything that surprises us. Okay, I call this as either you can call that the default, the default domain, or I tend to call it the natural domain. It's just because naturally, as a consequence, in the way how it's defined, how this function is defined with its operation, it can take any x value, any value for the input x, as long as the value is from the real number. So as a matter of as an interval notation, minus infinity to infinity. So just like that. So I briefly talk about natural domain. So think about this function. This function 1 over x, for example. Okay, and we should be fluent at this point to be able to determine the domain on any of these functions with its operation, with its expression, and we call that it's the natural domain. So think about g of x equals 1 over x squared. We've been through with this from earlier lecture that this function here has the domain. You see, and I have nothing special. It's just the way how it's defined. It has this domain minus infinity to 0 as open parentheses and union with 0 to positive infinity. Now I call that with a further term. This is the default domain or the natural domain. Okay, so now I refer to this as the natural domain. All right, just the usual domain that you used to see up to this point. Okay, fancy term, but because there's a need to introduce those fancy terms, or the default domain. All right, so fair enough with that understanding about what a natural domain is or a default domain is. It's like I said, it's just probably my own term that I'm using to distinguish with the later thing I'm about to introduce. All right, and so now allow me to put this function away, and let's get our attention focused back to this function f of x equals x squared. All right, so now I'm going to swing back to the graphing space, and we're going to look back at the graph. And so with this function f of x being x squared over here, because the natural or the default domain is all the way from minus infinity to infinity, that's why you can see that we can notice that horizontally this graph spreads all the way to infinity horizontally, and it spreads all the way to negative infinity horizontally. Okay, so that's nothing new. But now here's what I'm doing. There will be times where we only need, so instead of taking the entire natural domain, okay, so now I'm saying again, instead of taking the entire natural domain, which is all the way from minus infinity to infinity, there will be times in our applications, in our work, when we work with a function like this, there will be times where we only need a portion of that graph. Let's say positive x values only. Okay, so again, I repeat, there will be times where, depending on our applications, we only need to look only at the positive inputs of this function. Okay, and so the reason I mentioned earlier about we need to look back at piecewise function is because that idea has already been introduced back in the lecture where I talked about piecewise function. We have functions that are piecewise where, hey, there's a piece here where the graph appears to be a the function appears to be a parabola. There's another piece where the graph of the function appears to be a straight line. So quickly, as a demonstration, I just want to show you that the idea about, seeing, instead of seeing the entire domain, the entire default natural domain of a function, we're only seeing a restricted domain. Like this case right here, I just want to show that the idea is actually not new at this point when we're learning. We have seen that already. So for example, okay, we have seen piecewise function where, hey, it's a straight line, a straight horizontal line, and then it switched to a parabolic shape, okay? And then it breaks into a different piece right here. That's why it's called piecewise. And then it switched to another piece. 3 separate pieces, for example. So this parabolic shape only exists anywhere for x in this domain. Now, this domain may be from some a value to some b value. And this is what I meant by, we, instead of, see, the parabola itself, it's on its own natural and default domain. It's supposed to spread all over into a complete cup. Okay, but now depending on the needs, like say we have already seen that kind of application when we were working with piecewise functions, then we only need the parabola, we only need one piece of the parabola in an interval. And that interval now I refer to that as the restricted domain. Okay, so something like this. Okay, I refer to that as a restricted domain instead of the complete full domain, or instead of the complete default domain, we're only looking at the restricted domain right there. So now back on the graph here, back on the graph just specifically about the x squared function. Now, so again, the complete full domain is all the way from minus infinity to infinity. But now, as I'm pointing out, there will be times that we only need to look at the function, one piece of the function, where x values, in this case right here, anywhere x value is greater than or equal to 0, for example. So this is one restricted domain. Okay, so now back on this board. Now we can purposely define. So this is something that we can define. So first we consider this function, and we already knew that it had its own natural domain being this, but now we're going to purposely define. Okay, we're going to purposely define. We're going to define on purpose that I'm going to call that now, how about a function g of x. Okay, I just want to reserve that name f of x for x squared with its default domain. So now it's gonna still be the same. It's gonna still be the same x squared. So I define g of x to be x squared. But now I have to provide the restricted domain. So with this function, just like what the graph is showing, okay, with this restricted function, there are a couple of different ways how we can write it. There are a couple of different ways how we can write it. Now I need to write it a little bit further up so that so g of x equals x squared. But now one way we can write domain from 0 to positive infinity, and that's what I mean. That's what I meant by it's the same operation with x squared, okay, but then now it's a completely different function, and so it came from that function f of x, but now it has a restricted domain. So it's still that x squared function, okay, but instead of the usual x squared that takes the complete full domain, now it's just the x squared, the newer version of x squared. I named that g, but now this function here has the domain being compared to the original, compared to the full x squared, and this function is only defined as x squared on that domain anywhere x greater than or equal to 0, okay? This domain in interval expression, that's what it looks like. So as a matter of fact, another way of writing this, sometimes you will see a lot of times in textbooks actually, that they define a function g of x equals x squared, and then x greater than or equal to 0. They attach some kind of inequality about the input zones, the input domains right here. This is also indicating that, hey, this is our function, but it's not the complete x squared. It's only the function in that domain right there. It's only the x squared in that domain. If anyone wonders, so once I define this function restricted to this domain, and what about outside of that domain? Who cares? It's just, there will be, like I said, there will be times where we only need to work with the x squared function for the x values greater than or equal to 0. Okay? I'm saying what I'm about to say may be a little new for anyone learning, but who knows? Sooner or later, maybe some of you will end up with in business application, for example, where you apply a lot of your algebra skills here into doing your business. Okay? A lot of times when we come up with functions that model our business, then usually our function there is, okay, as a quick application, when we come up with a function to model our business, the variable here is a time variable a lot of times, and so for being time, then we only have time can only start when it's t greater than or equal to 0. That quickly demonstrates a quick application that we have a lot of times out there, function defined on a restricted domain. Okay, so think about your business. Okay, think about your business. Doesn't matter how you come up with your modeling function. Okay, to predict future, in the end, it always have to start out with time 0. Time 0 is whatever time instance that you started your business, and from that point on, as time goes on, as this variable value increases, right, your function may go up and down, but in the end, we only looking at a restricted domain. There's no such thing as a negative time amount. All right, and that's the idea. So just want to point out that the idea of restricting a domain does exist, and it actually exists quite often out there in our daily applications. Okay, so now in that way, now the impact of doing this, the impact of restricting from this original function failing to be one-to-one, because it, on its natural domain right there, on its default full domain, it goes all the way from minus infinity to infinity, and the curve was a nice parabolic shape. That's why it fails being one-to-one. But now look at what happened. Look at the impact once we have restricted the domain of this function down to only a small zone. The graph is still here that you can have a close look. Okay. The impact now is that once we have restricted domain, now this function, this piece of the function at least turns out to have turns out to be one-to-one, because now, after completely disregarding all of the other pieces outside of this domain, then this piece that's still here in front of us here is one-to-one, because any horizontal line passing through the graph, any one horizontal line here only passes through the graph at one point. Okay, and so now once we have restricted our function into a domain that has that made the function, so my point is, again, we turned the function, we restricted the function into a domain where it now appears to be a one-to-one, and from there we're going to start looking for an inverse. Okay, we're going to look for an inverse to this piece of the function, okay, on that particular restricted domain. All right, and so in that way, now I'm going to erase this part of my board here. So how are we going to find that? So I'm still illustrating that idea with the x squared function now, but so now we are given, just think about, we're done with f of x equals x squared, but now we're looking at g of x equals x squared again, but on the restricted domain, x greater than or equal to 0. Okay, so hopefully anyone is clear with that idea, right there. We're not working with the x squared in the complete domain, but now we're looking at that piece of the x squared function that's on this domain. And now consequently, at this point being only restricted to this domain, then it appears according to the graph showing, it appears to be one-to-one. Okay, so now in that way, okay, then let's find the inverse, okay, of g of x. And so now when we say g, we have to understand that it only takes this input, this domain right here. So let's find the inverse of g, okay? And it's a domain, okay? and its domain. So now when I'm saying its domain, I meant the domain of this inverse of G. Okay, the inverse of G, and its domain, and of course domain and range. The domain and range. All right. So now, at this point, we can start bringing in our understanding from the previous example. That was in example 5, where we learned to find the domain and range of, along with finding the inverse with domain and range given right there. Okay, so we're now going to bring back our understanding, our experience with the earlier example 5 right in here into this particular demonstration problem. All right, so now our function at start, our function is g of x equals x squared. But now we have to attach, we have to always attach along or bring along the domain. So the domain for this function is the interval from 0 to infinity, including 0. And then let me bring up the graph one more time. The range for this current function is still, anywhere from 0 vertically to positive infinity, okay, because the function can keep rising further up. All right, so now in that way, the range is just like what we used to know about the natural x squared, right there, the default x squared. So the range, okay, is that vertical interval from 0 to infinity, but including 0. So we have the domain and range nailed down on this. Now I am going to just apply the steps that we used to know about how to find inverse function. The only thing is, be aware that our function here is restricted in this domain and range. It's already restricted. All right, so step 1, I'm going to replace that symbol by y. So y equals x squared. Okay, and then the guideline says, the general guideline for finding inverse, because now we know that this function will have an inverse, at least on this domain right here, it will have an inverse, because we already saw through the graph, it's 1-to-1. All right, so now in this way, once we have arrived at y equals x squared, now the next step is to swap x and y, right? X becomes y and y becomes x. So now my equation here appears x equals y squared. But now that step, again, just like how I did that in example 5 earlier, this step is extremely important, is extremely critical anytime we have domain and range attached along the way right here. When we made that swap, okay, domain and range also switch roles, okay, the domain and range here, because again, imagine that this is x, and this is currently the zone for y, but now as we switch their role, as we swap their role, we have to update the domain and range. The domain this time for this, the domain for this function. The domain of the inverse is supposedly the range of the original function. So the domain now is going to be the previous range, the range of the previous function. Okay, and so just to be as close to example 5 as possible, I'm going to write the domain here, the updated domain, the switched over domain by blue ink. So 0 to positive infinity. But hey, it's not this one, it's the other one. It just happened that the domain and range for this restricted function looks the same. Okay? And then in the meanwhile, after we switch x and y, then the range is switched to being that one, that interval. So now it's also another interval from 0 to positive infinity. All right. But now just keep being aware of the domain and range after we make that switch right there. Okay. And then now I'm going to continue with the usual work. I'm going to solve for y. Okay. So now when solving for y in this particular problem, it's just the nature of the square operation. Now to solve for y, I'm going to have to take the square root. Because it was square, so solving for y here, I'm going to have to take the square root. And so now with our past understanding, solving for y here, yes, I'm taking the square root both sides, but that really means I'm going to have to end up with y, the square cancel with the square root, but now y equals plus and minus square root of x. That's the whole trouble that, without restricting the domain, then we're going to end up with two expressions. That's not making it a function. Okay, and I will get even to that even further. But see, so without restricting the domain, then usually anytime that we're solving for x equals y squared by taking square root on both sides, we will end up with y equals plus and minus square root of x. Two expressions. Okay, two expressions. That's not making it a function. That is the reason why now when it comes to this point, we're going to have to make a choice. We're going to have to make a choice. Now, the domain of this function tentatively is anywhere from 0 to positive infinity. Yes, that's perfectly consistent with the square root operation, because square root only takes the domain anywhere for x equals 0 to positive infinity. But now let's look at the range here. The range is supposedly the y value that's coming out from this function. If we had it, if we would use it, it has to be the expression that guarantees the y value falling into anywhere from 0 to positive infinity. So this is the decision line right here. This is the decision guideline for us right here. So I decide now, we now know a decision to make our correct choice. I have to go with, in that way, according to this range requirement, I'm going to choose y equals the positive square root of x. That's what makes it connected. So now I have to make a note here as a selection. As a selection, okay? We chose that. So solving for y, we're all in this kind of operation right here, it will always bring into two expressions. Y equals plus and minus square root of x. But in order to be a proper function, we can only have one function. I mean the expression equal to the variable y right here. And so now to make the correct selection, we're looking at that range requirement. This range requirement is saying that I want to choose between the two expressions here, I want to choose the one that guarantees a positive y value, okay, and at least 0. The only way we land into this. All right, and so now at the final step right here, so once we have made that selection, that decision to select that particular expression, now our inverse for g, so g inverse now is concluded to be, okay, positive square root of x. We have found the inverse. So it takes an entire unlimited world to talk about inverse function, but at least here I don't want my students to go out there in the world and say simply square root of x is the inverse function of x squared. That's false. Square root of x is the inverse of the x squared function only in that domain x greater than or equal to 0. Square root of x is the inverse of the x squared function, but only in that restricted domain. All right, only in that restricted domain. Okay, and so now that illustrates enough the idea that this is one big long demo over here, but now at this point we are ready for driving it into some formal example. Okay. So now at this point, all of a sudden, we've learned that excellent detail that allows us to overcome that challenge about finding inverse is only for one-to-one function. It's still true. I'm not making that understanding a lie. I'm not turning that understanding that we've learned that we had previously into a lie. I'm not turning that into a lie, but now I'm saying we have a way to work around with functions that are not one-to-one. So we can purposely restrict that function into an interval. Okay, and then in that interval, tentatively, the function will appear to be one-to-one in that given interval. From there, we are going to find the inverse, but only applicable to that restricted domain of the function. All right, so now let's walk ourselves into example number 6. All right, so now let f of x be defined in the given domain. Okay, so now find the inverse, okay, of f of x, okay, and its domain and range. All right. And that is our example number 6 that we're starting. So now the idea is that we're going to walk through a few problems where I call part A, part B, part C. Okay, it all depends on how much creativity I have that pops out from my mind about these different functions. Okay, but now on any of these functions, I am going to give a restricted domain to ensure that the function is only one-to-one inside of that domain, in that restricted domain. So let's get to it. And then from there, we're going to find the inverse. All right, so how about let's stay right here with our x squared function. But now, how about f of x is the x squared function. But we want to be working with the domain that's x is less than or equal to 0. Okay, so really this is chosen. I mean, somebody who defined this function chose this domain for us. So x squared by itself has that natural complete domain being all the way from minus infinity to infinity. But now we define a function, or at least we're given this function that was already predefined only in that restricted interval, x less than or equal to 0. Or in another way of saying this is another way of saying this is minus infinity comma 0. That's in interval notation. Okay. All right, so before we get our hands on this function, let's quickly have a look at the graph, okay? All right, so again, this is the graph of the complete x squared function, the complete full x squared function, where the domain is that natural default domain that goes all the way from minus infinity to positive infinity. All right, so now I am going to look at just that piece where x is less than or equal to 0. All right, that is the piece right there. This is the piece of the graph, the piece on that parabola where it shows it's the f of x equals x squared, but only when x is less than or equal to 0. Only for x value less than or equal to 0. This is what it is. X equals -1, we have a value. X equals -3, we have a value. What about x equals 1? It's undefined because we don't know what's the definition for x equals 1 on this function. This function is only restricted to this interval, to this the domain anywhere less than or equal 0. All right, so in that way, now we are ready to get our hands on to it. All right, so with that function, I'm going to make a note right here. I'm going to change the domain indication here into interval notation. So this is the domain, okay, and then the range here is, now we have seen on the graph earlier, from 0 to positive infinity again. 0 to positive infinity, okay, and this is the domain. All right, so now here's the work we're going to start out by finding its inverse. Because we saw on the graph earlier, this function now in this restricted domain, it will be a one-to-one function. It is a one-to-one function in this domain. And the range we saw on the graph earlier as well, the graph was vertically spread anywhere from y equals 0 and up. All right, so now in that way, again, just the usual steps right here. I am going to replace the symbol with the y variable. So now y equals x squared. Okay, and then in the next step, I am going to swap x and y, or interchange x and y, or switch roles between the x and y. There's so many ways we're seeing it. Okay, so y becomes x on the left-hand side, and x becomes y on the right-hand side. This is the reason why now domain and range have to also switch. All right, so at this point, just like how we did in example 5, for this going to be inverse, okay, I am going to, or right at this step, I am going to say that for the going to be inverse, the domain will be, see, the domain of this going to be inverse will be the range of the previous function before taking inverse. So that means the domain is going to be from 0 to positive infinity. It's that one. All right. And then the range, on the other hand, right at this step, we can already switch the range here. The range has to be that interval. The range of the going to be inverse must be the domain of the original function. Okay, so now the range here has to be anywhere from minus infinity to 0, including 0 in interval notation. And that's why I wrote it in blue ink right there. All right, and so now at this time we are ready to move on with the solving steps. Now I'm going to solve this equation for the y variable, for the variable y. At that step where we already switch x and y roles again. Now I'm going to solve for y. Okay, so solving for y again. In this way, how it appears right now, y squared equals x. So solving for y, the only choice we can make, the only operation we can apply here, take the square root on both sides. So that means and taking the square root on both sides, I am going to end up with y, because square root cancel with y squared. But now square root, but that will give me plus and minus square root of x. Okay. So anytime we're taking square roots on both sides of an equation, we have to do that, plus and minus square roots. All right. So now again, we ran into that very similar situation as how I was doing that demonstration earlier. We facing that decision line right there. We need to decide which one, because right now there are two expressions that can possibly equal to y. So we need to pick the correct one. We need to make the correct selection right here. So what's the decision? We need to pick between the two expressions here, positive square root x and negative square root x. We need to pick the one that satisfies the range here, the output values, y values being anywhere 0 or less. Anywhere 0 or less for the y value. So that leads to we must choose y equals the negative square root of x in this case. That's the reasoning. That's the logical argument of that. All right, and so now in that way, we have found that inverse function. So now I can say inverse, okay, f inverse of x is negative square root of x. All right, now we have found it. And the domain here are these, okay, domain and range. That's what I've done. And so again, I don't want my students outside of my class to go out to the world and say minus square root of x is the inverse of x squared. That's false, because it's not entirely true. Okay? Minus square root of x is only the inverse of x squared on that restricted domain from minus infinity to 0. Because you also have seen earlier in the demonstration problems, positive square root of x was also the inverse of x squared, but on the restricted domain from x equals 0 to positive infinity originally. So now in this function x squared, we're restricting that to the domain from minus infinity to 0. Okay, we come to that inverse being minus square root of x. All right, so before I'm leaving this part A right here, allow me to swing over to the computer to demonstrate the graphs. So the graphs, just like any other examples, the graph of the original function, I'm going to draw that in. I'm going to use a red color, and I'm going to print the graph of the inverse function here in blue color. All right, so now this is back on our graphing space with the function of with the the function f of x equals x squared restricted on the domain anywhere less than or equals 0 for x. And so now this is now going to be the graph of the inverse function. Here's the 45-degree line, and as expected from our previous learning, we know that the blue graph, once I put it here, it has to be the reflection of this red curve through this 45-degree line right here. All right, so here we go. Let's have a look. All right, so there it is. That's the graph. Okay, that's the graph for. This is the graph of minus square root of x. And it appears to be the one in blue right here. It's exactly the same curve, same scaling. It's just the reflection of that red curve through the 45-degree line. All right, and now let's look at part B of the example. All right, so now in part B, once again we will be given a function with a restricted domain, or there will be, for any of these problems, there will be a domain that comes along with the function, okay, so that we can put into our awareness. All right, so part B, how about let's work with f of x equals absolute value of x minus 3. Absolute value of x minus 3. Okay? Absolute value of x minus 3. And then here we want to work on that function, on that domain where x is less than or equal to 3. Okay? Have some time writing it down. Okay? And so now once you finish writing it down, here's how we start. Let's have a look at that. The graph before I proceed. All right, so this is our empty graphing space again. This is the graph of f of x equals absolute value of x minus 3. Okay, it's a V shape, that seats its vertex right at x equals 3. Okay, but in the end, the major difficulty with this function is that it fails to be a one-to-one function, and that is the reason why now we are going to restrict that into a restricted domain. So this is the complete now. So to remind anyone, this absolute value here function, in the way how it appears, it looks like the natural complete domain of this function is all the way from minus infinity to positive infinity. Okay, but now we are going to restrict the domain to whatever given and written on the board earlier. We're only looking at the graph here for x less than or equal to 3. Okay, so in that way, in the restricted domain. All right, so in the restricted domain, that's what the graph looks like in the restricted domain. And so now, obviously, once we have restricted the domain of this graph here, the function will become one-to-one. Clearly seen here because for any horizontal line, it only crosses the graph, this piece of the graph here, only at one point. Okay. And then further, before I switch back to the writing board, this function here, this function on the restricted domain here has range from anywhere from vertically from 0 and up, vertically. Okay, and so now we are ready for doing some work. So I am going to rewrite this. Ideally, if I have more board space, and I would completely write the function, the beginning function here, again here with the domain in the interval notation, but here I'm so short at space, so I'll have to erase and write it down. So domain here for this function is anywhere in the way how we read the graph, minus infinity to positive 3. That's the domain. And the range of this function. The range is anywhere from 0 to positive infinity. Okay, so we saw that right through the graph. And so now let's get our hands to it. So to find the inverse, what we need to do, once again, first step, I'm going to replace the symbol by the y variable. So y equals absolute value of x minus 3. Okay, y equals absolute value of x minus 3. Okay, and then in the next step, again, just follow the guidelines. In the next step, we are going to switch x and y. So x becomes y and y becomes x. So y becomes x in the next step equals absolute value of y minus 3. Okay, y minus 3 in absolute value equals x. Okay, y minus 3 in absolute value equals x. Okay, and then right at that switching point right here, right at that switch point, then now we are going to look at the going to be domain and range. So domain of the going to be inverse is going to have to be the range previously. So the domain at this point will be updated to switch to 0 to infinity. Okay, and the range for this going to be inverse has to be anywhere from minus infinity to 3. Okay, this is the zone for all the y values that tentatively we want to get out of this equation. All right, so now here it comes another algebra that you probably need to reveal if you feel, unfamiliar with what I'm about to do here. But now the range here, the range in blue is indicating y value tentatively once we switch. Okay, tentatively the y value must be anywhere less than or equal 3. This also means y is less than or equal 3. That's what it is. So for absolute value, this expression in absolute value must equal, you see, so as a reminder, this is a property from algebra. Doesn't matter what expression that is, but say y minus 3 or whatever, but y minus 3 in absolute value. This will equal to y minus 3 completely without absolute value, no negative signs. But this is true, this absolute value expression is only equal to y minus 3, simply just that, but only for y greater than or equals 3. But then on the other hand, this y minus 3 in absolute value will be equal to the opposite of y minus 3. The opposite of y minus 3. That's why I put y minus 3 in absolute value, in parentheses with the negative sign in front. So this absolute value will equal to the opposite of y minus 3 anytime y is less than 3. Okay? And then this equal sign can actually be used a little loosely, because in the end, if we put the equal sign here and skip the equal signs there, they're all going to come to the same value anyway. So for our particular need right here, I'm going to use the equal sign for that, even though it shouldn't matter. So now this is the perfect, this description here matches with our current y value requirements that we came out from switching the domain and the range. All right, so it is extremely important that you bring all of your understanding from the previous course in here. This property about absolute value that I just introduced as scratch work on the other board should have been learned from your prerequisite course with them. Okay, and so now apparently on the right hand side here, instead of writing y minus 3 in absolute value, now I'm going to write that as minus and then y minus 3 in parentheses equals x. Now we can start solving for y, because right here at this step we never learned any technique how to solve directly an equation that involves absolute value. Okay, so we have to get the expression out of the absolute value, and now we can start solving for the variable that we're looking for as usual. Okay, and so now the negative sign is going to distribute. So that's making it x equals a negative y plus 3, and now things become easy. So I can start speeding up the steps a little bit or skip a couple of minor steps right here. So in the end, we're going to come up with y equals, right? By solving for y will equals minus x plus 3. Okay, so y equals minus x plus 3. There's only one expression that equals y. And so now allow me to use this board to continue the work. And so now in the next step, I'm going to say f inverse of x is equal to minus x plus 3. Okay, and then the domain and range here, the domain is anywhere from 0 to positive infinity, and the range is anywhere between negative infinity and 3. All right, and that's the end of our work. So again, I really hate that anytime my students coming out to the world out there and saying minus x plus 3, I really feel unsatisfied if my students tell audience out there that minus x plus 3 is the inverse of absolute value of x minus 3. Nope, that is not. That is false. Okay, the correct way of saying minus x plus 3 is the inverse of absolute value of x minus 3, but only when we restrict that function here in the domain between minus infinity to 3. That's the correct way of saying. Otherwise, saying simply just minus x plus 3 is the inverse of this function, that is entirely incorrect. Okay. All right, and so now on the graph, this was the absolute value of x minus 3, but restricted to the domain anywhere less than or equal 3. And so now let's look at the inverse. The 45-degree line is here. Okay, and so the inverse now will be this line right here. All right, so the blue and the red will interfere each other at this point right here. Okay, but then the blue and the red are exact mirror image of each other through the 45-degree lines. And so at this point, this example 6 is still easy in a sense that so it's just getting anyone comfortable, and it gives a clear understanding for anyone viewing the lesson about once the function has been restricted, once a function which was known to be not one-to-one, but now once we restrict that into a domain that made it one-to-one, then we can go ahead and proceed and find the inverse function based on the updated restricted domain. Okay, and of course, once we, just like I said, once we restricted the domain, we turn that into a one-to-one function in that domain. Okay, but it actually, the good impact of this example right here is that when you are in that position, when you define your own function, say I was a student once and now I'm a teacher, I can now flexibly define my function by restricting an interval to reach my need to teach that, hey, I can make that function one-to-one in that domain. Okay, and so students can do the same thing. So now once you have seen through this example, I will take you into another problem where I want to lead you in a way that, hey, for any function you can, and of course for any function at start that appear to be not one-to-one, we can purposely choose. So like I said, here I chose these and created those as examples. And many textbooks authors do the same way. Okay, they come up with a function completely not one-to-one from the beginning, but then they purposely chose an interval for the students to read through and work through as examples right there to find inverse and all that. Okay, and then eventually it made students think that that's only the work for the authors who write textbooks, okay, or for professors who teaches. Okay, but in the end, one day any one of you learning from this lesson will also is expected to know how to handle that on your own, to be able to come up with your own domain, making the function one-to-one. Okay, so now let's head into that next example where we're gonna leave it for your own choice. Okay, so I'm gonna pretend that I'm just a student like anybody in front of the camera here. Okay, so allow me to first write down the worded instruction of the problem first. And forgive me about this next example that the wording may not be clear at some point, but I will try to be as I will try to give in as much explanation as possible. Okay. Actually, I have to completely erase this. All right, so let's now call that example 7. Okay, so find a domain. Okay, find a domain. Find a domain of f of x where f of x is 1-to-1. Okay, find a domain of f of x where f of x is 1-to-1, and then find the inverse of f of x in the restricted domain. All right, find a domain of f of x where f of x is 1-to-1. Okay, and then once we found that domain, once we're happy with that domain, all it needs is we pick a domain. And that's the important part. When it says find a domain, I can choose a domain as a student. If you're a classmate of mine, you can choose a different domain right there. Same function. You can choose a different domain as well. As long as we meet that requirement, we make our function 1-to-1. And then once we restrict our function into that domain, then we're going to find the inverse of our function f in that domain. All right, so the work will carry those steps from example 6, but then it has something extra on top, in the sense that we have our own control about how we can choosing the domain right here. So this is sort of like revealing a secret for students to know how I've been coming up with those domains for you to find an inverse function on those functions that are not 1-to-1. Okay, so now part A. Simply, I'm going to just look at, how about I'm going to go back to my favorite function, f of x equals x squared. That's it. We have a function suggested here, and now we got on this function given, we are going to find I'm going to pretend that I'm a student, and I'm going to pretend as students, and I'm going to pick an interval. All it needs is the interval of I'm going to pick a domain. And all it needs about the domain is that my function x squared here gotta be 1-to-1 in that domain. All right, so let's have a look. So I'm gonna swing over to the graph. This function is easy enough that anyone should know the graph of that, and it's among the toolkit's functions. Okay, so all right, so here we are in the graphing space with the graph for x squared already present here. Okay, so think about this. All we need is to pick a domain. All we need is to pick a domain where this curve here appears to be 1-to-1. Because right now the complete full curve is not 1-to-1, fails a big time to be 1-to-1. So I can pick a domain that anywhere from -3 to -1. This domain right here, in between these two value, okay? Anywhere between, see, between the two vertical grid lines right here. Okay. That's one of them, that's the low, and that's the high, okay? So anywhere between this, the function, once we focus our the attention to this, to the piece of the graph inside of this domain, anywhere from x equals -3 to x equals -1, this part of the graph is 1 to 1, okay? So if I was a student choosing an interval like that, that's fine. It meets the requirements. It meets the requirements that the interval is making our function f of x 1 to 1, okay? And that's for one student. For another student can pick. Let me quickly adjust this, the two vertical lines right here. Any other student can pick a restricted interval anywhere from 1 to 5, okay? That works too. Okay, so in this interval from 1 to 5, our piece of the graph here between that is obviously 1 to 1 again. Look at any horizontal line here. It will only cross the graph in this domain at only 1 point. All right, and that is how we can become creative. So allow me to stick with that initial choice right there in that restricted domain from -3 to -1. Okay, so now it's the function, but now I'm going to choose. So this is the given function, but let's stay with the worded instruction. As a student doing this problem, I'm going to say, we're going to choose. So think about your instructor grading this paper. No one can be unhappy about what you choose. As long as you meet this requirement, you chose an interval, and it made your function 1 to 1 in that interval. That works, okay? So this choice may be different with your friend's choice, your classmate's choice, but as long as you made it satisfy this requirement, it's gonna work. Okay, so as a choice here, I chose it's a little bit improper writing, so I chose to work with the interval x anywhere from -3 to -1. Okay, I purposely chose the interval that's, you know, as weird looking as possible, as negative as possible, but it's gonna turn out nice. Okay, so now in notation, in interval notation, the domain here is chosen to be anywhere from -3 to -1 inclusively. And now we can either use the graph or just use a calculation here. What is the range for this chosen domain right here? What can it be for the range for this chosen the domain? All right, so back on the graph, recall for yourself again, the range is the vertical spreading of the graph. Okay, when we're in that domain already, so now if we're in this domain, the range is here, from here up to that height right here. Okay, and so now that means the range here, right here from the graph, reading the grid right here, okay, then that gives me from anywhere from y equals 1 to y equals 9 right there. Or mathematically, we can also do the math right here as well. You see, this graph is entirely going one way, and one way I mean it's only falling down, either falling down or in a different interval it's only going up. Okay, that's how it's connected with being 1 to 1. So now 1 to 1 in this domain, the function is going one way down right there. Okay, and so now in this way it's going down only from the left to the right, and so that means the right has to be lower and the left is higher. With all that I was saying, then we can quickly find that, you see, the function x squared, but now at -1. The right end of the interval is -1 all squared. That gives me +1. Okay, and then the function at -3, the left end of the interval, of the domain interval, that gives me -3 all squared. That's 9. So and we saw on the graph earlier, it's falling from the left to the right. From the left to the right, it's falling. So the range here, well, the range, it's just simply an interval that describes the function. So now in the end, the range just high value on the right, low value on the left. So the range is going anywhere from 1 to to 9. That's the range of this same function, but when we are restricted in this interval from -3 to -1. Now you got the function with the restricted interval, your choice right here, your choice. And then the range came out consequently. Okay? And now I'm going to use the space on my other board right there to work on the function to find the inverse. Okay? And along with the domain, okay, on the restricted domain right there. All right, so now here we go. This function of ours right here, it's x squared, okay? But now we know that we're only working in the domain from -3 to -1. We chose this one as a student. We chose that one. And then we work with what we chose. The range here is the interval, the vertical interval, anywhere from 1 to 9. All right, so we have the domain, the restricted domain, and the range that came out consequently. So now, just back to the usual steps of doing our function here, finding our inverse function. So in this restricted domain, first of all, I'm going to switch that. I'm going to replace that f of x symbol with the y variable. So y equals x squared. That's my first step. And now I am going to switch the roles of x and y. So y becomes x in my next equation. X becomes y in my next equation. And at that point, once I have done switching, again, remind yourself, just like example 5 that we've done quite a little while ago in this lecture, then now the domain and range get switched too. The domain now for this going to be inverse has to be from 1 to 9. And the range, okay, the range for this has to be anywhere from -3 to -1. Okay, so this is the new domain, the domain on the going to be inverse, and this is the range of the going to be inverse. Okay, and so now, and we're gonna go ahead and proceed. Continuing with the steps, now I'm gonna take square root of both sides because it's quite familiar equation right here. So I'm going to take square root on both sides. That gives me y equals plus and minus square root of x again. And I'm saying again because it's just like many of the examples we've done earlier. And now at this point right now we have two expressions that can possibly equal to y. And that's where we need to make a decision. Okay? And so the decision comes out, whatever decision we have to make, it has to be consistent with the range right here. See, look at the range. The range for this tentative inverse or for this going to be inverse has to be this range. The y values have to land into this interval anywhere from -3 to -1. -3 to -1. But hey, -3 to -1 in the end, the whole complete interval here, the entire complete interval here must be a negative interval. Negative interval. Think about the y value, the y-axis. -1, -3 is down here. So the whole interval, but in the end, the entire interval sink below the x-axis, being a negative interval. That means to satisfy this range right here, where I want the y values coming out from this to be inside of this interval, the only choice I have to make. So now that leads to my final decision. That has solid fact right here. We have to choose y equals negative square root of x, because that's the only way making our output value, our y values, negative. And then that in this domain right here from 1 to 9, then it's going to fall into a range anywhere from -3 to -1. All right, so that's we land to that choice. We landed on that choice because of this range. All right, and so now once we're there, then we now can use the symbol f inverse of x to equals minus square root of x. That's making our inverse, and we purposely chose a restricted domain right there. Okay, so now let me put that on the graph right here. So on the graph itself, let me now, so make note of these two lines right there. These two lines that define our interval of the restriction. because I'm now going to hide them away. And now, see, so let's make it real clear. All right, so now in that restricted interval, our function is clearly 1 to 1. So now in that way, let's show the inverse. The 45-degree line is here. Okay, and now let me put it in a far zoom view right here. All right, so now for the inverse function, this is what it looks like. That's the inverse function. All right, this blue piece right here is exactly the mirror reflection of this blue curve through the 45-degree line. All right, and that's how we found. That's how we first of all chose for ourselves. A restricted domain. We chose it. Okay, and then from there we worked from the restricted domain. We would consequently come up with the range of our beginning function based on that restricted domain, and then from that point on we were able to find the inverse function. Okay, and so now think about this same problem. Before I'm getting out of this problem and moving to a part B, for example, then the choice of restriction, as I said earlier, it's pretty much the choice of anyone doing the problem. So restricting that to -3 and -1 is just my choice as a student. Okay, anybody else can have a different choice, but a choice like this on the graph would be wrong right here. Again, keep in mind our goal is we want to restrict that into an interval where we're making it 1 to 1. Okay, so now think about on the graph here. Now I'm going to put away this inverse function. Okay, the choice as following will be incorrect. If we choose, so this is the complete full x squared. But now if we choose to restrict in an interval from -1 to 2. So why is this wrong? As a matter of fact, on any function, it depends on our application. We can always restrict that in any interval we want. Really, any interval. We have our right to restrict that into any interval. But the reason this interval we restricted is wrong because it does not meet what we need. Our chosen interval here did not meet what we need. What we needed was an interval of restriction that made our function 1 to 1. And so obviously in this interval, the way how the graph is showing, has it been 1 to 1? Is it 1 to 1 yet? It's not, obviously. Right here there's a horizontal line that crosses the graph at 2 points. Any horizontal line in this area here will cross the graph at 2 points. And so for other applications, maybe this restricted interval will be good, but for our particular problem here, this restricted domain will not work out because the function is not yet 1 to 1, is not 1 to 1 in that interval, and that's why choosing something like this will be incorrect. All right, and so now let's give it another try. Okay. Now in part B, let's look at a different function because we've worked with the x squared function long enough. And so how about we are given f of x equals 1 over x squared. 1 over x squared. Okay, and let's have a look. So it's just starting out being a function given. Let's now look at the function on the graph with the graphing utility here. All right, so with my blank graphing space right here, this is the function 1 over x squared. Okay, so apparently right at the beginning, this function appears to be not 1 to 1. It fails to be 1 to 1. See, a lot of horizontal lines cross the graph at 2 points. Okay, so now we are going to purposely choose an interval on that graph to make it 1 to 1, and the interval itself is again on our choice right there. Okay, so back on the graph itself, now I am going to, okay, I'm just going to pick an easy one. So how about I'm going to pick from 1 to 3 right here. Okay, from 1 to 3. All right, so now pay attention to the restriction I have just set. I'm going to restrict the domain. Okay, the natural domain is all the way from minus infinity to anywhere less than 0, and then unions with anywhere between 0 and positive infinity. But now, like I said earlier, I am going to restrict the graph into the following domain, anywhere from 1 to 3. Okay, so that's what remains right here. The same graph there, but now in this restricted domain, it's now 1 to 1, but it's only a short little piece of graph. Okay, but now this is a good one because it already meets the requirements. It's making our function 1 to 1 in this restricted domain. All right. And so now on my board right here, I'm going to write it down. I chose as a student. Okay, so anyone else can choose a different interval as long as it met that requirement, as long as you meet that requirement. We're making that function 1 to 1 in that chosen interval. Okay, so now we chose. All right. To work with x is greater than or equals 1, but less than or equals 3. That's what we chose. All right, so now from this point right here, that means I'm going to use the other board right there. But first of all, before I get on the other board, let's look back at the graph again. So now in this chosen interval, the function is clearly 1 to 1, and in the way how the picture looks, it's decreasing, it's falling from the left to the right, it's getting lower from the left to the right. Okay, and then we can look at that information here to find out the range of this function inside of this restricted interval. All right, so let's do a little bit of math here. So for x on the left end, when x equals 1 on the interval, okay, our function will be, the output y value for that will be f of 1, and that is equal to 1 over 1 r squared, which is 1. Okay. On the right end of the restricted interval, on the right end of the restricted domain, it's f of 3. The y value there is f of 3, which is 1 over 3 squared, which is 1/9. So now our range here, obviously, is obviously that interval. Now clearly or numerically 1/9 is lower value than 1. So now I'm looking at 1/9 to 1 as the interval that describes the range of our function. Okay, so now we are ready to really use that other board on the next, next space on the other board right there to get our function tackled down. All right, so now let's summarize our information. The function we are given is the 1 over x squared. Okay, the domain is now chosen to be in this restricted interval, anywhere from 1 to 3. That's our domain, our restricted domain. Okay, and then so from that restricted domain, consequently, our function came to the following range right here. The range came out only to be anywhere from 1/9 to 1, including the two endpoints. All right, and so now we have all that information we need. The interval was chosen as a student. I chose it. Anybody else viewing the video, you can also start having fun choosing your own domain as well. Okay, and then come up with your own range like that. All right, and so now let's get to it. So I'm going to start getting into hunting for that inverse. So I'm going to replace that f of x symbol with the y variable. So now y equals 1 over x squared. Okay, that's the first step. And now I am going to switch the roles of x and y. So y becomes x in my next equation, and x becomes y in my next equation. So in my next equation, I have x equals 1 over y squared. But now again, we have done this often enough, so I hope it starts nailing down in your understanding. As soon as we made that switch right there, and anytime we're working with with a domain coming along. Make sure we also switch on the domain and range like that. So now for this going to be inverse, okay, we're going to have the domain for this tentative inverse. It's going to have to be anywhere from 1/9 to 1. That's our going to be domain for the going to be inverse. And now the range, okay, will be, see, so these two just simply swapped roles as well. So the range for this guy, for this going to be inverse, is going to be 1, 3. That's what it is. That's what it is. Okay, so now we're going to, once we've had this here, we're going to hang on to that for a little while. But now let's get back to the steps and continue. All right, so now on our work, to solve for y from here, I am going to rearrange this. Okay, algebraically we know that we can cross multiply. And then after cross multiplication, we're ending up with x y squared equals 1. Okay, and then from this point right here, from this point on, we're going to divide both sides by the x variable. So dividing both sides by x, I'm looking at y squared equals 1 over x. Y squared equals 1 over x. Okay, and then in that way, now I'm going to take square root on both sides. And gosh, that's famous word keep coming back at us. Anytime we're taking square root on both sides, it's going to produce for us the following. Y must equal plus and minus square root of 1 over x. Plus and minus square root of 1 over x. Okay, and that's the reason why we need to start making a choice right here. We need to start making a, actually, so logically, we have to first make a decision between these two right here. That decisions come from this range right here. So the range says y value has to land into this interval, anywhere from 1 to 3. But in the end, 1 to 3 is a positive interval, or y value anywhere in this interval has to be a positive y value. Positive y value. Imagine that vertical y-axis again. 1 is here, 3 is here, okay? These are the y values that we expect our inverse function to land into, okay? But in anyway, it's a positive interval. Any y value here is positive above the x-axis. All right, and so now that's making it clear that now we must choose. Now we're going to choose. So as the next step here leading to, we have to choose y equals positive square root of 1 over x. Positive square root of 1 over x. All right, and then alternatively, this can also be written as 1 over square root of x. Okay, and so now we have arrived at our final inverse function. Now I can call, so I'm running a little narrow in space right here. Okay, but f inverse now of x, okay, is 1 over square root of x. That is our final inverse function. Okay, but again, I don't want any of my students to come out, to the world outside of the class here and say 1 over square root of x is the inverse of 1 over x squared. That is not true. Okay, that is false. As a matter of fact, okay, because here 1 over square root of x is only the inverse of 1 over x squared. Or how about, let's put it this way, 1 over square root of x is the inverse of 1 over x squared only when 1 over x squared is restricted in that domain. Okay, it's only, for now it's only true in this problem because we restricted that in that domain right there. All right, so that's how it happens right there. And then that's how we've done this problem. We purposely chose, right? And again, I chose this interval as a student. Anybody else can also choose a different interval. So for example, back to the graphing space. This is the current interval that I chose as a student. The complete graph is here. Okay, and I can choose a different interval. Say, okay, now let's look at that interval. See, somebody else can choose an interval from -5 to -1. This interval is again making it 1 to 1. Okay. an interval like this interval, we'll make it incorrect because our function still fails to be 1 to 1 in this interval. This interval from -5 to 1, and it has a jump in here. Okay, and so now that's how we've done these problems. Okay, and so look closely at the application of these the applications of these kind of problems out there. All right.